Now, let's take a look at what happens if we do a finite element seepage analysis instead of the water surfaces. So I'm gonna come in here and we're going to solve the same problem that we had before, but I'm just going to get rid of this material boundary, make it all nice uniform again. So the way we would do this is go to project settings, and we'll go to groundwater, and then instead of water surfaces, we would do steady state finite element analysis. Also, you may be wondering if you did a flow net and you wanted to import a grid, how would you do that? Well, you would come here. You import grid, total head, or grid pressure head, or grid pore pressure, or whatever it is. And that's where you would read in an Excel file or paste numbers into a table. But we're just going to go straight to steady state finite element analysis. Okay, and then here's the pore fluid unit weight. There are some advanced options here. So you can do transient groundwater. So steady state is where the flow condition is not changing over time. Water's flowing through your slope, but the nature by which that water's flowing is stationary, meaning that the flow regime is always the same. That's not always true, right? And during a storm, water will rise up suddenly on one side of a levee and the phreatic surface will gradually work its way through. You can model that here using transient groundwater. We're not going to do the transient in this lesson. Okay, there's the negative pore pressure cutoff as well. So if you have negative pore pressures above the phreatic surface, you can click this button to prevent those negative pore pressures from contributing to your slice equilibrium. So I'm going to go ahead and click that and do 0. So anything that's above, well, any pore pressure that's less than 0 will just be set to 0 in the method of slices. Okay, now what you'll find is that you've got two tabs here on the bottom. One is the slope stability tab. That's where you can do things like specify your circular grid, specify your mechanical material properties like the strength, C prime and phi prime, and the unit weight. Then there's a steady state groundwater tab, and this is going to be for a whole different set of parameters. This is for the finite element seepage analysis. So the first thing we're going to do is specify our mesh, and I'm going to click that button, and I'm going to go with 4-node quad elements, just because that's what I showed in my lesson. It turns out for seepage, you could use 3-node triangles or whatever. Any of these elements will work for you. I'm just going to pick this one, and let's do more elements than that. We'll do 10,000 approximate elements. Then you can push discretize, and it will put these little red crosses all along your boundary and mesh, and it's now done. You've generated your mesh. You can zoom in here and take a look. Here's a bunch of little elements. I guess there are some triangular elements mixed in here among the quad elements. So I'm going to zoom all again. And then let's zoom window again and look at what it's doing. Notice all these question marks, right? Those question marks mean we don't know what the pore pressure is along those boundaries. We need to solve for it. Now these boundaries have nothing, right? The vertical boundaries along the edges and the horizontal boundary at the bottom. If there's no boundary condition at all specified, then that's a zero flow boundary. There's no water that's going to flow down through the bottom or out through the left or out through the right. So I might have to actually make my domain a little bit bigger to get a reasonable result, because, for example, if this water were allowed to just continue flowing horizontally, if it's going to go through from left to right, then we would want to put this vertical boundary a little further away from our domain so that it doesn't start influencing pore pressures within the levee where the slices are going to be. Okay, so what I'm going to do next is come here, and this button is set boundary conditions. And I'm going to set the total head boundary condition to be 7 meters along that horizontal boundary right there. It was hidden a little bit behind this window. But anyway, I was setting it to boundary segments. So it's going to take that whole line and put the total head to be 7. Now what I'm going to do is boundary nodes and zoom in here like this. And I'm going to put the cursor like right at the top of that reservoir and then highlight from right to left. And now it's going to pick all of those nodes that are below 7. and we've got our boundary conditions specified. Now in the problem that we've been solving, the water table was right at the surface also on this side. So let's do that boundary condition too. Okay, the elevation at that location is 4 meters. So now we have to set the total head to be 4 meters because by default the datum is at 0. So now I'm going to pick boundary segments again. Click on that segment, and now we've got 4 meters there. And you don't see any kind of standing water because the elevation is right there. It'll plot this standing water anywhere that you have the water table above the ground surface. Okay, and then we will zoom all right there. Now, when you specify the material properties, they're different in the steady state seepage. You don't have strength, you don't have unit weight, you have permeability. So the default permeability is 10 to the minus 7 meters per second, which might be something like a fine sand or a silty sand. Then there's this K2 over K1 parameter. I mentioned that soil often has a horizontal hydraulic conductivity that's bigger than vertical. And this is how you can specify it here. So K2 is going to be, well, first of all, you specify this angle theta. Usually we would want that to be 0 so that, you know, we're specifying the one direction as horizontal and the two direction as vertical. And then you can put the vertical to horizontal permeability ratio, which is generally going to be smaller than 1. I'm going to keep it as 1 for now, just to do an isotropic seepage analysis. So I'll keep the default parameters for permeability. Now you've got this little compute button here for groundwater. So if you want to, you can run the compute. Let's save it. I should have saved this as a different file name. All right, I've overwritten my previous file name. Anyway, now what we can do is go here to our interpreter, and we've got contours of pressure head shown here in this little rainbow grid. You can plot total head if you wanted to. So here's how the total head is dropping from the left to the right. Notice that it's pretty much 7 meters when you come over here. It's like somewhere in that range. It's pretty much 4 meters when you come over here, and then it's decreasing in between. So let me show you a cool thing. Here you can do display options. Let's go with, let's see, not this one. This one. Is it that? No. Contour options, groundwater. So you can do filled with lines. Okay, now we've got a whole set of equipotential lines, right? Because these lines are denoting regions of constant total head. So we've got our equipotential lines drawn. Then another thing you can do if you want is to add, let's see, data. They've changed some options here. There's a way to sketch flow lines. Let's add a flow line at, so I'm going to just come in here and let's see, we've got to pick a point that's going to generate approximately a square, like right there. Maybe we go a little bit further down, right here, and come right here. So what I'm doing is trying to sketch a flow net here, kind of the cheating way, right? It's really hard to draw a flow net, but you can use your finite element analysis to draw one if you want. Okay, and then if we zoom out, you can see we've got this nice, pretty nice looking flow net here that we've sketched. So you can see how powerful the finite element analysis is, right? It would have taken really a long time to draw this flow net by hand. I could have done it a lot faster if I wasn't talking at the same time that I was doing the analysis, but you can see really kind of how quick this is and why it's becoming such a popular option. Okay, let's go in and just see what happens now. What's the difference if we do make the material anisotropic? So I'm going to make the horizontal permeability 10 times bigger than vertical, or the vertical a tenth of the horizontal. Do the compute. We'll save it, and it's going to take a little bit longer now. Did it already compute? I'm not sure it can. There it goes. Okay, now it's calculating. All right, so it finished pretty quickly, but it's a little harder for it to do the problem with anisotropic permeability. Oh, the computer crashed. Okay, anyway, here it is, right? It did work. It crashed for a second, but you'll notice that the phreatic surface is now a bit higher. Previously, it kind of came down and exited, not at the toe, but a little bit higher than the toe. Now that the horizontal permeability is so much bigger, it's going more like straight through the levee. So that's a bad thing, right? We don't want water to exit the face of our levee. Okay, and then now we've done the steady state seepage. We can go to the slope stability, and we've got this. So some aspects of the seepage analysis are here. It's showing that reservoir, but anyway, we can do the calculation. I'm guessing the factor of safety will be less than 0.992, which is what it was with the line drawn down. Oh no, that's what it was with that artesian pressure down here. It was 1.6 with just the line drawn down. Now that our phreatic surface is exiting way up here, the factor of safety should have gone down relative to our previous analysis. And indeed, it's only 1.473, so we get a slightly lower factor of safety here for this one. I would want to look separately at this point. If you come in here and look at the angle at which that water is exiting the face of the levee, you would want to do an infinite slope analysis there to make sure that your factor of safety is not lower than 1.473. It's really hard for the computer program to get a surface that's right there, and it may not test that surface, and you might actually get a piping failure. So the computer doesn't always get it right. But anyway, you can see how easy it is to do a finite element seepage analysis and combine it with your method of slices to get a factor of safety.